So now we're going to look at another game that leads to hugely fast-growing functions, also due to Friedman. And it's variously called the tree function or the just TR for short function. And there's various variants of this. And I, as usual, I'm not an expert at all. Um, but this is one variant that Friedman talks about in a paper called Enormous Integers in Real Life, where real life means the real life of a mathematician. Um, but it means not constructed for the explicit purpose of being enormous integers, and sort of unexpectedly enormous integers or enormously fast-growing functions. And the easiest place to get to it is if you go to the Wikipedia article on Kruskal's tree theorem and look at the references at the bottom. And I know that's not a very stable permalink kind of thing. Hopefully it will just stay there. But anyway, that's the title of the article. So it's another game, or puzzle, I guess. You could make them into games by making them two players and try to figure out how to like fox each other out of and like force each other into traps or something like that. I haven't figured out exactly how to phrase it that way, but it's just a new puzzle and involves graph theoretic trees. Okay, so just like a graph is a bunch of vertices connected with edges, a tree is a special kind of graph that kind of looks like a tree. And often we have them kind of growing upside down. So a tree looks like this, where here's the root, and I know that should be at the bottom, but I tend to draw them going like this. So here's some branches, and going off to the leaves. Okay, and each one is called a node, just like another term for graph, for a vertex, node or vertex, and the extreme ones can be called leaves. So various tree-like arboreal terminology. We're going to talk about rooted trees, which always have a single root node here, and so they can only branch as you go down. And notice I've kind of put them in somewhat carefully arrayed ranks here. So these three are special because they have just one. You only have to go one link up to get to the root. These guys, you go two up to get to the root. These guys, you go three up to the root. In other words, the number of direct ancestors of this is 3. The number of direct ancestors of this is 2, etc. So you can rank them by how many direct ancestors they have. Okay, so that's the kind of graph we're talking about. And just like with the finite integer sequences thing, we're going to try to grow a tree bigger and bigger in a way such that earlier parts of the tree, so parts toward the top here, don't match in a certain way with later parts of the tree. And the rules are kind of specific in order to get the particular version of the function he's talking about. And there's some variations, as I say, about exactly what the rules are and how much you decorate the trees with various labels and things like that. But I'll try not to worry us about that, again, mainly because I don't know the details, and because we don't really care. We just want one version that has been guaranteed to produce enormous numbers. Okay, so here's the terminology we need. Okay, let me show you what we're trying to avoid. Here's a tree. Okay, and I'm going to use a little more mathematical terminology, but I'll spice it up with some informal terminology. So this is a tree T, and this is level 0. The root is always going to be level 0, and so that's going to be T sub 0 is just that single node. It's a very simple little tree. T sub less than or equal to 1 is everything with one ancestor or less, and so that's this guy. Okay, and there's different conventions as to how you label zeros and ones, and I think I'm accurately using his conventions. It's not, I don't think it's super important to get the numbers right, although it might be. And then this is t less than or equal to 2, which in this case is the whole tree. Okay, now we also want to pay attention to the leading edge of each of these subtrees. So this is a nice subtree, t less than or equal to 1. Just this part here, these two things, that's T1 itself. That's everything with exactly one ancestor. And then here, this is T2, everything with exactly 2 ancestors. So it's just the 0th rank as you write them, as you draw it carefully going down, the first rank, the second rank. Okay, so what we want to avoid is something that's actually displayed here, which is an embedding of this tree here, an early tree, so that's t less than or equal to 1, a partial version of the tree, everything up to rank 1. And what we've got, the analog of a match between simple strings in the sequence game, is that I can map everything in here to the next subtree, t less than or equal to 2, in a way that satisfies two important things. One is that everything in the actual front rank, the bottom edge of this subtree, is supposed to go to something in the front rank of the bigger subtree. Okay? So that's part of what makes it a match. And then the more important thing is that it's what it's called inf-preserving, which is a little more sophisticated than what we've had to deal with before, but it's not that weird. Okay? So the inf, and I'll explain the terminology in a second, the inf of, like, say, two nodes, or vertices, I'll call them nodes, like n1 and n2, is the most recent, and I'm going to switch my metaphor, totally mix my metaphor. These can also be thought of course, as like family trees, right? Except without, like, I guess, of amoebas, because there's no sexual reproduction. The most recent common ancestor, okay? Or the most recent joining of branches, okay? This is short for the Latin infimum, which is a synonym, if you've ever taken, like, a basic real analysis class, which I'm not assuming. This is the greatest lower bound. And so the way you think about that is you think there's like an ordering on these things, that this is less than this is less than this, and this is less than this is less than this. And the greatest lower bound, so for example, let me give you an example. This guy, let's say this guy here, is the inf of these two guys. Hopefully that's pretty clear from this terminology, the most recent common ancestor. So when I say inf, and you think most recent common ancestor, or closest place that as you go up the tree that they both join into one, that's what it means. It's related to this very general notion of greatest lower bound, or infimum, the Latin, by saying this is less than this is less than this, and there's nothing else that's greater than this that satisfies those conditions. Like this guy is also less than this is less than this. In other words, it's just above it on the tree. But it's not the greatest one. It's not the closest one. So most recent is the greatest part. Common ancestor is the lower bound part. In any case, that's why the terminology. But I think it's good to just think about this in terms of families and stuff like that. Okay, so what do I mean by, so it's supposed to be an inf-preserving embedding. Okay. That's the kind of match, remember, that we're really trying to avoid. We better know what it is in order to avoid it. So this has an inf-preserving embedding, a match that we're trying to avoid, that these three guys, if I just map this to this, and this to this, and this to this, then what is it doing? Well, first of all, it maps the front rank here into here, and it doesn't, in the embedding part, means that it's one-to-one. The whole thing should not collapse any nodes to any nodes. And in particular, these two nodes should not be collapsed into one. That's not legal. Okay? And I'll say a little bit about why this is a reasonable rule and not just a totally artificial game in a second. So these two are going to these guys, and this guy maps to here. So what does inf-preserving means? It means that for any two things in the input, that's these three things in this guy. Ooh, let me show you a better picture here. Sometimes it's helpful to draw two copies of this thing. It's getting really busy with my marker here. So I'm mapping this to this over to here, and this to here. Okay, so it's really, I'm just trying to take this guy as a subtree and map it into this whole thing. The front rank maps to the front rank of the bigger guy. And it doesn't combine any two things into one, so it's one-to-one. And it's inf-preserving because, for example, the inf of these two guys is this guy, and where did those go? Those went to here, and the inf of those is this, and that's where this guy went. So it preserves that notion of common ancestor. A simple case of the inf is, suppose I have one thing that's actually a direct ancestor of the other. then the inf of these two guys is always just the ancestor. So that's an important point, is that means that if this guy goes to here, this guy is absolutely forced to go to some descendant of it somewhere. And so descendants, this in particular, means that descendants have got to go to descendants. And so whole chains and whole families have to be preserved. Okay, so basically in inf-preserving embedding, when you do enough examples of it, you start to see that it's really kind of just preserving a natural pattern in a tree. The trees have different looks to them of, is it like something that's a complete binary tree that like always splits in two, or is it a complete ternary tree that always splits in three, or is it something that splits in half and then goes single? These kinds of patterns are basically, if you have an inf-preserving embedding, it's basically saying, can you find one pattern at an upper level that's repeated at a lower level as the tree gets bigger? Okay, so obviously we need a lot of examples of this. And I'm not an expert in just kind of looking at one of these things and saying, oh, there's a match there, or not. Okay, so here's what we're here's the definition of the tree function, and we'll explore it. And probably not all in this video, I don't want it to be too long. So tr of k, okay, so what's k? In the n of k function, it was how many symbols we allowed ourselves. Here, k is the max number of branchings from each node. It's called the valence. It's almost the same as the valence in graph theory, but it only counts the downward branchings and not the ancestor branch that everything always has in a tree. Okay, if you know what valence is for graph theory. Okay, so, and this is going to be the max number of vertices such that there is no match, and match meaning inf-preserving embedding, from t less than or equal to I into t less than or equal to j for some 1 less than or equal to I less than or equal to j, and certainly less than or equal to, let's call it the, what's the terminology? Let's just call it the rank. I don't think that's the right word, but the rank of the tree. Just the how far they go down. Okay. So that has an E in it. Some has an E in it. Okay. So I hope the similarity to the sequence problem is clear, somewhat clear. That there we had a certain way of matching earlier substrings to later substrings, and they were just particularly special ones. This is actually a somewhat more, less contrived problem, I think. That this notion of a match is really a pretty natural one, the more you play with it. And we're just saying that if you look at only the stuff in the tree up through rank I, and then you look a bit further down to I plus 1, I plus 7, I plus 97, or whatever, can you find a match that takes this part, this initial part of it, to this bigger initial part of the tree? Okay, and we want to know how big can you get until you're forced to have a match. And of course, it's a non-trivial theorem that you are forced to have a match. That's the basic Ramsey theory type result here, and that's a version of what's called Kruskal's tree theorem. That there does have to be a match eventually, and the question is, how far do you have to go? Okay, so let's just do two very basic examples, and then we'll hold off on the more complicated examples and a description of how fast this grows for the next one. So tr of 1. Okay, as usual, start really simple. Okay, so I start with a root, and now I don't allow myself to branch except just going down. Okay, I can only just go down, and that's it. It's just going to be a line of nodes, and we'll see how far it goes. Well, here there's T0 is just this guy, and T1 is just that guy, and there is no T2, and so just for trivial reasons, that's legal. Okay, but now, if I extend it even this far, we're dead. There's T1, there's T2, here's T less than or equal to 1, so that's a subtree, okay? And again, I'll produce a separate copy of it. So if I just map this guy to here, leave it alone, and map this guy to here, then that's a match. So notice I can skip nodes, okay? I've just put this node in here and this node in here, and all I need to know is that the inf of the two resulting nodes, is where I sent the inf of these guys to. Well, the inf of any pair that's just one is an ancestor to the other is just the ancestor. And the ancestor here of this guy went to this guy, which is the ancestor of this guy. And the fact that there's a node in between is totally okay. That is not disallowed by this kind of embedding. Okay, so it's rather like the subsequence idea, the match idea in the sequences. You can delete nodes in between and kind of collapse everything and say, okay, the shortcut is like that. That's a copy of this tree when you kind of take shortcuts. Okay, so you're allowed to take shortcuts is one of the important things. Okay, so that means this is 2. At least by my exact definition, the variation that I'm using of TR. In any case, it's a very small number. Okay, but that's of course because we didn't have much freedom to do anything. We couldn't branch. Okay, now k equals 2. TR of 2 equals what? Okay, so first thing is it's not too hard to see that it's pretty useless to start with 1 and then branch. Okay. And in fact, there's a general thing that if, so here's a fact, okay, if a certain t is illegal, if it has a match, in other words, then adding at the last rank of t, adding nodes and branchings at the last rank of t or beyond, like adding stuff even below the last rank, is useless. It's still going to be illegal. There's still going to be a match. Okay, so that's a good one to think about for yourself, is that if you have a match already, you can't make that match go away by adding stuff at the end of the thing. You can screw it up. You can make it not work by adding stuff at the start, because the way the matches go is the earlier stuff has to go into the later stuff, and everything has to work consistently. But this is a good thing. Okay, so like here, this was the thing that didn't work with one branching. I've just added something, branching and adding something at the last rank, and that still doesn't work. It's easy to see that, again, there's t less than or equal to 1, and it maps to this, for example. Okay, so that's not useful. So it means we really, as you might expect, we better use that branching right away, that ability to double branch. But it still doesn't get us much. Okay, that's legal because there's no T2. Okay, and this is legal for a very simple reason. Remember, I've got to take T1, and I'm supposed to take that to the new front rank. So this is t less than or equal to 1. So I'm supposed to take this subtree and map it into t less than or equal to 2, because it's the only other subtree I can consider. And these two are supposed to map to this guy, but they're supposed to map 1 to 1, and that can't happen. Okay, so that can't happen. That means this is legal. Okay, but that's about all we can do. Okay, because another fact is that, so that's like fact 1, fact 2, we can never extend every leaf, those ending nodes. So if we got something that's legal, like this guy was legal, if we extend every leaf by anything, by 1 or 2, let's just display 1 here, then what I can always do is I can just slide every single, I can keep everything at the top above. No matter how complicated the stuff is before the last rank, I'll just slide everything in the last rank down. And then all the ancestor relationships are preserved up here, no matter how complicated it is. So let me do one that's more complicated. Double, double, single. Okay. Now if I extend everything down, okay, This goes to here, this goes to here, this goes to here, this goes to here, this goes to here. That's the map. Everything else above stays. Then it's easy to see that all the ancestor relationships are fine, and everybody has a place to go. Nobody has to crunch together 2 to 1 or something like that. Okay, so you can never extend to every single leaf simultaneously. So that means if you've got this one that you know is legal, yes, you can do this, but you can't put one on both. Okay, and what's the only other thing you could do? You could say, oh, I'm going to extend one of them twice and split it off. Remember, I'm not allowing any triples yet because this is k equals 2, and we'll do that next. Okay, well, look at what happens here. This guy can map to this guy. Okay, and that's, I kind of picture that as sliding this down. Take this double split and slide it down. That's exactly a good example of the picture you should have in your head of an inf-preserving embedding. So any double split like that, if that's the whole tree that I'm trying to match with, then that's just going to be, any double split is going to match that guy. So that tells you how limiting this is, that I know that just not branching at all is stupid. It's not very useful. But if I can only do double branches, well, this double branch, that's t less than or equal to 1. If I ever see this pattern of one thing splitting into 2 ever again in my tree, then I'm going to get a match. Well, that means I can't ever double branch either. Okay, so this is very much like n of 2 with the sequences. It's really, really limiting, okay, because this is the only, I've now excluded the only interesting thing I can ever do, kind of like with the 1, 2, 2, 1, 1, 1. Okay, the only interesting thing I can do is do 1, 2, something like that, and I run out of options here. Eventually, I'm going to have to put a 2, and okay, I'm screwed. Okay, so here, that's as good as you can get, and so that's equal to 4. Okay, now, in the next one, we'll do some examples with k equals 3 and get a sense, a little bit of a sense, of that does break the logjam, and it suggests at least that you could go pretty far.